Hello, Professor. This is me, Nadeem Saeed Baloch, with the student ID E9875. Today, I'm going to present my second research paper with the title The Google File System. There's a kind of scalable distributed file system presented or developed by the Google for its own services. Well, starting with the presentation includes, first of all, starting with the introduction. It's a kind of a brief introduction from the research paper. So, first question arises here: what is actual Google file system? Basically, the Google file system is a scalable distributed file system designed specifically to meet the demands of the data-intensive applications. What are the data-intensive applications? Actually, the data-intensive applications are those applications which need the high data sets to save or to process their streaming, just like we can see that the YouTube or which is using uh, the video streaming, and it needs to store the petabytes of the data for itself, for its algorithms, or for continuous streaming. So the purpose of GFS was, there was a couple of purposes of making it. First of them was handle the massive data set processing tasks with the high reliability. Like there should be a reliable data, there should be a reliability of the system, plus the massive data should be processed at the simultaneous time. So the second would be second was like operate in the inexpensive commodity hardware. Like the clients or the one who are using this service should not buy many kind of servers or any expensive special kind of desktops from any other organization. No, that was designed on for the purpose like it should be able to on the commodity hardware which are easily available, like the normal desktops and the servers are easily available in the markets. So there are some key features of the GFS. First of them is the fault tolerance to manage the frequent hardware failures. Like if your hardware is gonna trash, if your hardware is not gonna work, or still your data will be saved. This is claimed by the Google file system at the time of presenting it. Yeah. And the second was the high scalability, supporting thousands of nodes and petabytes of the storage. Yeah, the Google file system is actually work on that principle. Like there would be one master server which would be connected to the thousands of the nodes. They are called nodes. They are also like the servers, but they are called nodes. They are connected to the master. As the master instruct them to store the data or replicate the data or whatever the master wants to do that, they would connect it to the single master from that side. So the third feature is optimized for the large sequential read and append heavy operations. Sequential reads are those like if we are going to read the data or we are going to write the data, that should be in the it should be in ordered or in the mannered way. And append heavy operations means if you're gonna in the traditional file systems, if you're gonna add the data or you're gonna update the data, this they show the strict consistency, and they show some sort of updates in a very short time. Like for the Google applications, most of the times you don't need any kind of strict consistency model, because uh, Google prefers scalability in the form of, like, when it was presenting the Google GFS Google file system, it preferred the scalability over the consistency, because it claims that the data should be more accurate than that of fast. So if you're gonna update the data into the Google file system, it would gonna take like some time, but the data at every single node presenting to the every single client would be very accurate and the corrected one. This is claimed by the Google, so it's very significant as well, like because like JFS breaks away from the traditional file systems. It prioritizes scalability, fault tolerance, and the cost efficiency, which was a big lack from the previous traditional file systems. What was the actual problems statement which was addressed during uh, the implementation of during the revolution of GFS? The problem statement was the traditional file system couldn't handle the Google's growing needs, as the Google for search indexing, for web browsing, or for storing data. Uh, the traditional file systems, they were not able to meet the Google needs. So they were just struggling with the frequent hardware failures because they always assume that the traditional file system, they always assume that the hardware would always be okay for our data. They only just do work on the algorithms. If the algorithm is good, that's good. But in case of hardware failure, there would be no replacement. There would be no any chance to recover your data. But GFS addressed this problem very efficiently. The second problem was the massive data sets. Yeah, they were able to store the data and with the lower size. But in case of massive data sets with the sequential workloads, they were not able to do that. And the third problem was to improve the scalability. Yes, the data should be available in every single point, and you can update your data, and you can add more and more nodes if your data is going to be so big. So you don't need to replace your server with the another bigger one with the bigger size. You actually can update the server with the previous one. And the design goals were there were kind of 4 to 5 major points addressed while designing the Google file system. First of all was the scalability. Yes, the data should be scalable. The system should be scalable as your data increases with the time. Second, if your hardwares or fails, the data should be available to the clients. Uh, so this was also addressed in the case of fault tolerance. If we move on the high performance, so the sequential reads and the updating your data in the form of append heavy task, it shows the very good performance for the Google services. The cost efficiency was its architecture shows that there you don't need any much more uh, heavy equipments to make this storage system or the file system. Just if you're gonna grow your data, then that would be costing you the storage cost, then nothing more. And most efficiently, it's gonna work on your commodity hardwares which are easily available in the market. So relaxed consistency model, uh, Google file system basically is applicable on the relaxed consistency model, which claims that your data would be collected for the writing. You're gonna contact the master server, which says that your data would be you'll be gonna connect it with the master, and master will be just directing you to the primary chunk server where the data is actually saved for you. If you're gonna rewrite or update the data, your data will first would be analyzed, stored, and then it would be replicated to all the rest of server which are having the same data. Then it will be able to see then it will be able to present or to able to see the by the clients. So eventually they claim that the data would be corrected one. It would take time, but it would be finally eventually it will be corrected one. If we talk about the architecture contains three major core components, which are master server, chunk server, and the client. The master server basically manages the metadata, like the namespace of the file and the chunk replication, where the data should be replicated or not, and what's the file and the kind of identifier which is given to the client. And chunk server basically stores the file in size of 64 MBs for making uh, for making available every single time to the client. Handle data, chunk server handles the data for the reads and write and instructed by the master. If the client is gonna ask to the master that I'm gonna read the data, then it would be directed to the any of the chunk which has the data. It can just read the data. If you're going to write the data or update the data, then it will be directing you towards the primary data, a primary chunk server, which has ability or which has options to rewrite the data or update the data. And the clients are the third more important component, which is obviously want to read the data or interact with the uh, data through the following procedure, like first from metadata stored by the chunk server, and then moving from them to from the master server, then from to the chunk server, and master will be then directing these two connected nodes like the client and the chunk to each other for just specific tasks, either reading or writing data. Yeah, if we talk about the methodology in the methodology, there is first step, which is a file division. Files are divided into fixed size 64 MB chunks, each assigned a unique identifier. So if you want to read the specific portion of your data, you must have the identifier which is given to you or given to the client by the master server. So master server will only allow you to approach the chunk server when you'll be having that particular ID or the identifier. So metadata management is also done by the master server, and it stores the short time or lightweight metadata memory, which allows you to look up where the data is actually in which chunk server. It doesn't actually look up what the data is. It just connects you through the identification to the specific chunk server. And the data operations clients contact to the master for the metadata and then directly communicate, as I told earlier, for the with the chunk servers to read and write the data. And basically, it follows the master slave architecture. In case of our architecture, the master is going to be the main server, and the slaves are those who are called the nodes, who are storing the data and will be able to present the data on demand, or will be able to rewrite the data on demand. Here is a diagram which more efficiently elaborates how the data, how the client is going to be contact and read or write the data. If you're going to see my mouse, in the left side, there's application or the GFS client would just having an identifier in the form of file name or the chunk index. It would just directly contact it to the GFS master with the identifier. Like I have this username and ID and password. I want to read this uh, file from my whole data set or from any of the data set. I want to read this file with this identifier. It would be just giving you the file identifier to the GFS master. Then GFS master will quickly look up that where the data is stored, in which chunk server the data is available in this chunk server. It would be just asking this chunk server to be ready to present the data for reading, or to give the permission to the client to write the data. So the chunk server would be acknowledge this the GFS master, and GFS master will then give the location of the uh, chunk server to the GFS client, that you can now access that chunk server by this location, or then GFS client can directly contact the chunk server for the data reading or writing, or whatever update if they want to do with that. So in the simultaneous time, the rest of the chunk servers, they will be easy and they will be doing their own stuff. But if we are gonna write the data will be written here in the primary chunk server, which is allocated by the master. Then after the writing here, it would be updated to the is rest of the two replications, and when it's totally updated to everywhere, then it would be ready to present to the client, ensuring the correctness of the data. Here are some real life use cases of the GFS. GFS is being used in the search engine indexing of the Google, storing the lot of web pages in the form of petabytes of the data. And big data analytics is more inspired, like the sports frameworks like the MapReduce. It's really enabling like high throughput analysis of the massive data sets. Most of the times, like video streaming, video storage and the streaming, such applications like YouTube and these kind of applications which needs their data, their petabytes of the data to be stored somewhere in the smart file system. So here is also GFS is being used. Machine learning and AI models, they also use the GFS uh, and to like store the data because they need the data sets for training their model. And Google machine learning models, they use the GFS. So Cloud Storage Foundation was basically started from this concept of GFS. Now we are seeing a lot of cloud platforms by the Google. They're provided to the clients. So they basically work on this basic principle. Though GFS is a great revolution in the field of distributed systems, but still there are areas of improvements which are being addressed also. But in my case, I still think there are areas of improvement which need to be addressed, or which can be addressed. Well, I think the problem with this system is replicating your data, like each chunk with the which would be the primary chunk with having your actual data. They would be replicating 3 times across the different servers. So that would definitely increase the storage cost, and you'll have to pay more, especially for the massive data sets. For the low, it's okay. But the second problem is the centralized master can become the bottleneck in extremely large clusters. Yes, if you'll be gonna have the large clusters, then if there will be a number of clients, they are approaching the master for the single statement, for the single data. The master have to address every single client on the single on the same time. But there will be a problem for the master to address every single client, locating it to the primary or either replicated chunk server. That would be a challenge for the master, and that's how the problem arises here. But in my case, if I were to address these problems, my personal recommendation as per my research is, uh, first of all, addressing first problem could reduce the storage overhead by implementing the erasure coding. In erasure coding, what we actually do, uh, we can, if or in case of like failure data, we don't need to write the whole data sets provided by the clients. We can just data we can just write the data into the coding, and we can just, if in case of the system failure, we can just again recreate the data using the left behind data. So this is the core concept of erasure coding. I super extremely sure that it's going to work in the GFS file system also. And addressing the master's bottleneck, I would say, to increase the masters with the same capabilities. Like if there is a one master, we have to increase the number of masters as the number of chunks. It shouldn't be as the number of chunks. Yeah, chunks can be in the form of thousands, but if there is a single master, there should be at least like couple of 3 or 4, because they would be having the same capabilities. If the master with the single uh, with the multiple nodes is busy with some of the clients, so there should be a replacement which can also like addressed by another client, or the other clients can also be addressed by different masters. So this is how I think to be addressed these problems. Finally, there is a conclusion of the there is a conclusion for my presentation, and the conclusion is Google file system, from no doubt, like it's transformed the large scale distributed storage system, while focusing on the scalability, fault tolerance, and the performance. And we have like experience, we have just see that how these problems and how these parameters were addressed and how these goals were achieved. While it has some limitations, which always be there in the technical perspectives, it needs to be high in the storage overhead and handling the small files. GFS has been instrumental in managing massive data sets, no doubt, and has influenced some modern systems which are being used today. But the foundations, like the cloud and every single time, the GFS was the foundation for all of them. And GFS remains a key technology for the data intensive applications. Here are the final key questions from my side, as I have experience. The first question is, why does the GFS use the relaxed consistency model? And the second is, how does GFS ensures the fault tolerance? And I have written the answers of them here. So, Professor, that's from my side. I hope I have covered the things in the given time. So, yes, that's all from my side. Thank you so much.